Okay. Let's come back to our lecture.
Okay.
To practice how to do the Durbin-Watson test and Lagrange multiplier test. You'll take time to do it.
Yes.
Anybody want to show me how to do it? Anybody?
Professor, I think I got stuck with the Gradle.
Stuck with Gradle? Okay, then.
Yes. Maybe I can show you how I do it, and then maybe tell me where I get wrong.
Okay, all right.
Okay, I'll try to share it.
Okay, share it.
Okay, grid model 4 is Gradle.
So you haven't to share your screen yet. Okay, okay. I think I can see it now.
Yeah.
Yeah, okay.
So you can see it, right? This how.
Excuse me. Okay, you have to do the constant variable. There's no constant terms.
Okay, so
from the equation. So do it again.
I do the OLS, right?
Yeah. From the beginning.
And
Okay. We do it again from the beginning.
Like this. You can see all my screen, right?
Yeah, but this equation without constant terms.
All right. So I think I must miss it.
Okay, I think you maybe just mistakenly eliminate the constant terms.
All right. I see. Here.
Yeah.
Put here.
Okay, do the regression again with constant terms.
Like this, right?
I haven't seen the result yet.
I think you just only share one tab of Gradle instead of like share the whole screen.
See. Okay. Now let me see how to do it here. I think this one.
Oh yeah. Okay.
Is it right? Then I do the test.
Yes. Then for the excuse me. Okay. Do the test.
Yes.
Hit the
And
test.
do this.
Wow. I think this is a little bit different from my version, right?
Yeah, I think it's different. So that's why I feel confused about it.
Okay. Would you please do it? Okay. Okay. Excuse me. I know the reason. Okay. This is a time series data. Okay. By the way, I think I forgot to tell you. From Gradles, you need to identify whether it is a time series data or not. Okay. Great. I think I according to what you have done, then I think I know. Since I already imported the data, so I missed all those previous steps from the Excel file. Okay. So let me show that first. Okay. All right.
Okay.
So that,
thank you.
I'll share my screen. Okay. So in this case, means that I need to use the, okay, let me get out of all my Gradles. Okay, did you see that if I imported my variable, my data file, and using the time series, then I will have the description like annual, then full range is from 1960 to 1988. If you don't do the step, okay, no. Let me start it. I think I need to get back to my original data with chicks, okay? Right? Okay, this is chicks 9. Then after I use the Gradles, then I drag in, right? I drag this file. I'm sorry. I cannot do it. I have to drag in. It's so hard to drag in. Yeah. Okay. Then I hit OK. Then, did you see this one? The imported data have been interpreted as undated, means cross-sectional. Do you want to give the data a time series or panel interpretation? I need to hit yes. Okay, then I'll put it time series. Then I forward. And this is annual data. Then forward again. Then forward. Then apply. Okay. Then it come out with the time series data, and it will invoke all the functions which can be done using time series. Did you see that? So if I do this one, then I can run the regression model. Y and this P, C, P, B, and YD. Okay, and I hit OK. Then I'm using the test here. And I do have some functions which can be done using time series data. So Gloria, do you understand what I'm saying here? You know,
Yes.
you're using cross-sectional data, so you didn't, I mean, turn on which functions that time series data, those functions that can be used using time series data.
All right.
Okay, I'm sorry, I missed this step.
Okay, we'll see. I will try it again.
Yeah,
Thank you.
Okay. Thank you so much, Gloria.
Thank you.
You remind me those which I need to be done, but I forgot. Okay.
Thank you. We learned that. Thank you.
Yeah. If I still have some time in this meeting, I will just leave to all of you and to do the practice. Okay. And by the way, there's another assignment due 2 weeks from today. It's about the chapter 9, okay, which you have to do for this assignment is 2 parts. One is from exercise number 7. The other one is the econometric lab number 5. So which is all on in the page 320 and 329. 221. Is that all clear for all of you? The assignment due 2 weeks from today. And next week is our exam week. Therefore, there's no class for our class. And you just take time to do the assignment during the next week, and this assignment will due on April 28th. Is that clear for all of you?
Yes, ma'am.
Yes, Professor, you said the exercise will be the seven one and the two three the page 320, right? And the
21.
5.
20 and 21 from part A to part D. I mean, all the questions.
Yeah, the
Number
7.
Number 7, and as well as the econometric the lab number 5.
Page number 220 and 21.
Yeah, 20 and 21 up to 22 to 23. You know,
22 to 23. Ah, okay.
econometric
It's the
lab.
whole. So
Yeah,
is
the
the
number,
econometric lab 5 is whole page
yeah,
to 2000 223. Okay, I understand.
yeah. So from step 1 to step 7 for lab number 5.
Okay.
Number 7 is from A part to D part, mean all of them.
All right. Thank you. I understand it. Thank you.
Okay, so you need to make sure know how to work with either EViews or Gradles. Okay.
Yes.
All right.
Okay.
And let me continue to work on our section 9.5, which is the remedies for serial correlation. Okay, they're all involved in our assignments. Okay. The remedies for serial correlation. Okay, make sure that we are working with the pure serial correlations. Okay, what do we mean by pure serial correlations? Means the serial correlations is caused when the regression is correctly specified. So if you have any problems from the model, which may be omitted variables or the functional form, all this about the specification problems, you need to fix that before you fix the serial correlation problems. Okay, so the following two methods we're going to use in is you have to conclude that you have pure serial correlation. Then we can use these two methods. Okay, the first one is called generalized least squares. Okay, and this will be from our textbook 310. Okay, let me show some of the PowerPoint, which is easier for me to do the explanations. Okay. Okay. So we are going to introduce these two methods, generalized least squares and Newey West standard errors. Okay. And what is the generalized least square methods? Okay. And I think I need to use some of the equations from our textbook or from the screens here. Okay. So let's start with an equation, which is 9.18. And this equation has involved first order serial correlation. In other words, the ET, okay, epsilon T can be expressed as the first order expression, right? So this first order expression. So in other words, this equal to this. Therefore, equation 9.18 can be rewritten as 9.19. So just replace the ET epsilon T with the rho epsilon T minus 1 plus UT. Okay? All right. Now, go back to equation 9.18. If I multiply rho Okay, I multiply equation 9.18 with row and also using the lag by 1 period, means using the original t to t minus 1. Then it turned out to be the equation 920. Understand what I'm saying here? Times the row. Okay, times row of multiply equation 9.18 by row. So all the terms have row, but lag 1 period. Okay, so this one become to y t minus 1 and x1 is become t minus 1. Okay, now since equation 9.20 to 9.19, we do have row epsilon t minus 1. Okay, so subtract equation 920 from 9.19. So using this one minus this one. Using this one, 9.19 minus 9.20. Okay? If I use 9.19 minus 9.20, then this row epsilon t minus 1 will eliminate on both equations. Okay? So it turned out to be like this. There's no more zero correlation related for the error terms. Okay, any questions so far?
No, thank you.
So the generalized least square equation is do the estimation of 9.2021. So in our textbook, they're using new expression of 9.21 to 9.22. So all with the variables with the star signs is the new variables. And of course, with the star signs, yt star is equal to this original yt minus rho t minus 1. And this is a new concept, constant terms. Okay, and the whole things, this part is a new xit 1t star, and turn out to be this one. Okay, so from equation 9.22 is the equation without zero correlations. And it seems that, we can use the OLS. This is what least square, the name of least square coming from. But this is not original ordinary least square. Is generalized least square, which is different from ordinary least square, because ordinary least square should work with the equation with linear form. Equation 9.21 is not the linear form. Okay, this is not the linear form, because we need to estimate beta 0, we need to estimate beta 1, and also we have to estimate the row. Okay, and let's see. And you can see that this beta 1 is really from the original. The original is 9.18. This beta 1 and this beta 1 are the same, but the yt star, yx1t star, and also the beta 0 star is really different from the original 9.18. Okay, all right. Therefore, since this is the original beta 1, so if we are using generalized least square to estimate equation 9.21, the beta 1 has the same meaning as those estimated from OLS. I think this is the advantage. Using generalized least squares. And remember that this YT star is different from the original YT. Therefore, the original YT, the R square from the original YT, and the new R square from equation 9.22 are not comparable, since they do have different dependent variable. Okay? Any questions so far? Okay? Any questions so far? If you don't have any questions, then I will go on, okay? And there are a number of techniques that can be used to estimate generalized least squares. You know, maybe we can, the short name will be GLS. Okay, there are a number of techniques that can be used to estimate the GLS. Then our recommendation from the author is to use called Price-Winston methods. Price-Winston methods, I think the name is on our textbook, 311. And this Price-Winston methods contains two-step iterative technique. Okay, what are they? Which is on textbook 312. Okay, the first step is to estimate rho. And then the second one is use this estimation rho to estimate equation 9.21. I think this two steps will repeat it, iterated until the better result is coming out. Okay, and all this GLS equations use those iterative nonlinear regression techniques. It's really well beyond the scope of this class. Okay, maybe those PhD students, you will get to these methods in Dr. Lin's class. But here, well, I'm not going to say anything about this. Okay, I think the idea, okay, to estimate equation 9.22 or 9.21, okay, you'll know this one. The concept of this will be enough. And the rest of the procedures, I will just using eViews and Gretel's to show how to do these remedies. Okay? All right. So let me go back to the eViews first. Okay? If I want to do this test, okay, everybody, would you please, there's a footnotes from our textbook to tell us how to do from eViews. Well, maybe I'll just show you how to do it, okay? Let me go back to my data. Where's my data from eViews? Huh? Where is my data? Where do I get my data? Okay, let me do the estimation, okay? If I want to do this generalized least square from eViews, okay? Do you remember this one is the original one? I do the OLS. I would add one more term, which is called AR parenthesis 1 parenthesis. I need to add one more term, which is AR1 here. Okay? Okay, after I do this one, then I hit OK. Okay, did you see the output here? This is exactly the output also from our textbook. Equation 9.25 on page 313. And this is called the generalized result of the model, the chicken demand model, okay? And the one we added for x variables is the AR1. And the coefficient of this AR1 is this estimates is called rho hat. Just remember that generalized least square, we had two steps. One is, the first step is to estimate the rho. So the rho hat, the coefficient from AR1 variables here is the rho hat we estimate. Okay, using this rho, then, go back to the equation 9.21. Then we can have the result exactly like this. And I would say that all this coefficient from the x variables is the beta, right? So these are also the same as when we do from the OLS. The meaning is the same as we do from OLS. So 9.25 is the result using generalized least square method. And if we estimated this one and the serial correlation problem fixed, how do I know it? Look at the Durbin-Watson statistic here. This 2.05. You all remember the range of Durbin-Watson statistic. D equal to 2, close to 2, means there's no serial correlation. Okay? Is that clear for all of you?
Yes, ma'am.
Huh?
Yes,
Excuse me. Yeah, okay. Then this is by eViews. I'm going to show how to do the grados. Okay?
Professor,
Yes.
do we have to give the AR1 for definition, or just put it
This
there?
is uh this is the the procedures. We need to put AR1 here from in eViews. Then I think this program's already done, embedded inside the eViews. Okay, then if you put this variables AR1 here, then automatically they are using Praise-Winston methods.
Okay, thank you.
Okay, did you see? You all see the footnote from our textbook 312, the footnote number 16.
Yes.
Okay, I think I follow the procedure from our textbook. Okay, but if I do it from the e-views, I think you will know that, pretty close. They do have pretty close result. Okay, so let me show how to do the Grettles. Okay, let me see. From Grettles. Okay, how do I do it? I'm using model. Okay, now I'm not going to use an ordinary least square function. I need to do the univariate time series. Did you see that? Univariate time series. If you don't using the data with the time series data, you are not able to have this function. So remember, you need to have this function, okay? And choose univariate time series and choose the one with AR arrows. Did you see that GLS, generalized least squares? And I'm choosing AR1. Did you see that? Okay, then my Y variable is Y. Okay, and from Grettles, there are 3 methods, and Price Winston is in the middle one. So you have to choose, let me have this one lower. Okay, you have to choose this one, okay? Y variables and X variable, and choose this one and hit OK. Okay, let's compare this result with the e-views. Did you see the row here? AR1. And for Grettles, did you see the row? 0.5632. And for e-views is 0.55656. It's pretty close. Okay, it's really pretty close. And by the way, the coefficients is somewhat a little bit, somewhat different. Okay, but I think the significance is the same. Okay, so this is the way to show Price Winston methods using Grettles or e-views. Is that clear?
Yes, it is clear.
Okay, I just, excuse me. I just show it once that, the model, but choose the univariate time series. Okay, and choose the AR, GLS, and AR1. You will get the result. All right, so those of you, either you can use e-views or use Grettles to work on our assignments. Okay, it really doesn't matter. Either one of them will be okay. All right, this is the first methods about generalized least squares methods. Okay, and the second way is called New Way West Stand Arrows, and which is shows on our textbook 313 up to 314. And you'll remember when we study the heteroscedasticity, there's a one way to fix heteroscedasticity is using white standard arrow. You'll remember that? then the idea to use the white standard arrow means that since the consequence of heteroscedasticity, one of the consequences is the standard arrow from heteroscedasticity problems is the standard arrow is biased. Okay, but the beta is not biased, is unbiased. Therefore, they just fix the standard arrow only. So the same idea for time series data. If we have zero correlation, then the new West standard arrows just take account of zero correlations without changing those coefficients estimation themselves. So the idea to use new West standard arrows are similar to the white standard arrows.
Professor, can you
Yes.
repeat again?
Okay, you all remember that when we do the cross-sectional data, and one of the remedies is using white standard arrow. You remember that?
Yes.
Yes.
And the reason for that is because if we have heteroscedasticity, the beta, I mean the coefficient of the equation is unbiased, but the standard arrow is biased. So in other words, if we can just fix the standard arrow from the OLS, okay, then we can fix the heteroscedasticity. Okay, so the same idea for zero correlation is that if the equation do have zero correlation, one of the consequence is the consequence for zero correlation is the beta is still unbiased, but the standard arrow is biased. Therefore, New West using the same idea is just the white standard arrow to fix just only the standard arrow. And that makes they will fix the standard arrow instead of and let the coefficients stay the same. So new standard arrows can be used for also the t-test and other hypothesis testing. In most of the samples. And you will find out that New West standard arrows usually, because New West considers zero correlations, therefore the New West standard arrow are larger than the OLS standard arrow. So in other case, it will produce lower t-scores and also decreasing the probability that all this hypothesis testing, the significance of the hypothesis testing. Do I make myself clear? Do I?
Okay, Professor.
Okay, so let me show you how to do using eViews and also Grados, okay? Why don't I just start it from Grados, okay? And for Grados, I'm using ordinary least square methods, okay? Y, and with 3 variables. And remember, this one, robust stand arrows. Okay, if you hit this one, for time series data, okay, there are several functions. Usually we're using HAC, and I'll tell you why we use HAC, although the result is not that quite clear, but this, you choose HAC, okay? I don't think we have to do this one, and hit OK, HAC, okay? Since this is time series data, so they were used for series data, HAC, and hit the correct. Okay, then OK. Okay, this is using Newey West standard arrows. But I'll use, I'm sorry, I put this result here. Okay, and I'll this one. Okay, then let me use the eViews. Okay, estimate for eViews. I also go back to the original OLS methods. Okay, now I need to change the options. You'll remember that we do it for heteroscedasticity. We choose white, right? To do the white corrections, white standard error corrections. But now for Newey West, we're using HAC. This is the Newey West is HAC. So that's why in Gradles, I'm choosing HAC. Okay, so I'm choosing HAC and hit OK. So this is the result. Okay, let's compare this one with the one using Gradles. Okay, did you see the result for all of them? This is from eViews. This is from Gradles. The standard arrows is still a little bit different, okay? So t-value is a little bit different, but you know, for significance is quite okay. Okay, this is more easier than generalized the least squares, but both ways is popular. And I think this one, you know, from our textbook, equation 9.26, this result is from another program called Stella. Okay, I don't think, you know, this for coefficient, there's no problem for coefficient. And the difference is from the standard arrows, a little bit different from the standard arrow. But if you use up to 2 decimal places, there's no problem with that. Okay.
Yes.
You know that for today's lecture is, you know, more complicated than before, especially for those eViews and Gradles procedures. Okay, if you have any questions, you know, since we don't have class next week, okay, go back and review all these recordings. Okay, then if you do have any questions, okay, do not hesitate to ask me using the lines.
Okay. Professor, may I ask maybe a very silly question?
Why? What is that? There's no
Why, if Because I think there is a number, I mean, we want to know the relationship of the time series, right? So why we want to remedies for the serial correlation? I think they have connection with the time series, right? I think there are a serious number or data why we want to remedies their connection, their
Well, because
correlation.
because we are using OLS methods so far.
Yes.
Even the New West is just using the OLS, but correct standard error. And if we use the OLS methods, one of the assumptions from OLS methods is called there's no serial correlation problem.
Ah, I see.
Yeah,
Ah,
for
okay.
time series data, if they involve time, most of the time series data involve serial correlations, just like
All right.
cross-sectional data involve heteroscedasticity problems. So if we use OLS methods, then those estimation, the result is not reliable.
Right.
So all these remedies is to fix those problems in order to have the OLS estimations to be reliable.
I see. Understand it. Thank you very much. It's
Okay.
pretty good. Yeah, thank you.
Okay. Any other questions?
Prof, for the homework, Prof,
Huh? Excuse me? No
for
problem.
the assessment, and then the lab 5, we have to see the lab 2 in chapter 3, right?
Oh, you mean the data?
This is the question is, as an economic lab 2,
But if you check with chapter 9,
yeah,
CONS, let me see the, okay, let me see our data, okay?
econ,
This is our data set, right?
yes,
So if you come from this chapter 9,
yes,
there's a,
yeah.
I'm just using eViews, okay? The CONS 9, okay?
Yeah.
If you turn it on,
Yeah.
this is the one. Oh, what? This is the one we are going to use, right?
Yes.
So the Y variable will be CON01.
Yeah.
And the X variable is DPI,
Yeah.
AAA, and year.
Yes.
Okay, so it's CONS 9. You can use this data
No.
set.
Yeah. I mean, what the relation between lab 2 and lab 5, Prof? Because they
Oh, let me see. Lab 2.
yeah.
So let me see the lab 2. Okay, let me see lab 2. Okay, lab 2. Okay, excuse me. Is this the one from chapter 3?
Yeah, chapter 3.
Okay, let me see. Chapter 3. Use. But there's no data from here. Huh? Well, chapter 2, I don't have any data from here. Well,
Yes.
I think it is pretty similar. But maybe it's not the same thing. BPI. Oh, it's pretty similar. It's pretty similar, but actually the data set is from chapter 9.
Oh, I see. Okay.
Okay, just
No need
use
to use.
because you cannot find the data from chapter 3.
Yeah.
Okay, all right. So just get it from chapter 9.
Yeah.
And
Okay.
and using the CON as 9.
Yes. Okay, bro.
Okay,
Okay. Thank you, bro.
all right. Then any questions now?
No,
No, bro.
Okay.
thank you.
No problem,
If
That's it.
bro.
there's no
Bye-bye.
question, let's go back to let me see. Let me go back to and let me stop the recording. Okay.